Welcome back. We'll resume. Of course, the first lecture only dwell into the reliability equation, which is going to be modified because of the preventive replacement decisions are to be taken under the preventive replacement and the corresponding FDP equation and the stabilized failure rate and corrective, that is corrective failure rate or replacement rate or so. So those are very applicable. Now we are coming to the optimizing maintenance and replacement decisions. When the component is going to be replaced, there could be the possibility it can either be replaced because of its own age or because of the system age. So depending on that, the models have been created and whether what we are trying to optimize, whether it is the minimization of the cost, operating cost and replacement cost, or minimization of downtime. So based on these four models can be formulated. And so this, to start with, clearly define the question. If you are in research, this is one of the issue, how to define the problem. If you can define the problems, and then the next question to be answered, how to model it, so that it can capture the scenario for which model is to be created, and then we search for the methodology to solve that model. Another aspect, make the model no more complex than necessary to answer the questions to be answered. Okay, these are some of the saying by the experts in the area of maintenance or area of management. So if you see the various areas which can be dealt in the maintenance engineering, one could be the component replacement decision, inspection procedures, capital equipment replacement, resource requirement, and so on. And we are basically dealing with in this lecture uh, this area, right? Partly this area. Okay, partly we are going to deal with this. Of course, the software people have created the software also, which are given in this house, right? You can find the software if you're buying the corresponding book by Jardine. You may download those softwares. The component replacement decisions, which is covered in this area. The squeaking wheel does not always get the grease. The time comes when it needs a replacement. Okay, so common confusion I have already covered in my last lecture, right? So the component comes under preventive replacement policy. Then what is the best time, which we'll see how to model. Two types of problem, deterministic and probabilistic. Deterministic, I have given you example of filter replacement or belt replacement or any other which can be replaced in a time bound manner in expectation that the performance is going to be improved. So just see that examples of that. Okay, the cost is increasing. If you know the cost, if you can formulate a cost function for that, and the cost is increasing, and at one point of time you are going to replace it, right? So it involves the operating cost, which is varying with time, and the replacement cost, which can be taken on an average constant, right? And usually we take the short time decision, long term decisions, in the sense that these replacement might be in a month, in a year or so, not like 15 years period or 20 years period, the life of the equipment, where we take the capital equipment replacement decisions, which are, those are based on total cost criteria. 15-20 years, you also know that the cost also varies. Inflation to be incorporated, deflation is to be suspected, and based on that, the models are to be modified. And as the money changes its value over a period of time. But for a short duration, for 1 year, we expect that money is not changing much. No, interest rates are increasing. Inflation is almost coming to a constant or so. This slides again I have covered in the previous lecture. So coming to the first model for a deterministic, where we say that some equipment or item operates with excellent efficiency. For instance, the filter when it is new, but as the time goes on, the ages and their performance deteriorates. Cost, in other words, the performance in terms of the cost is going to increase. So the question becomes, when is it economically justifiable to replace the filter, thus reducing the operating cost? of the automobile or any other item. So replacement costs money in terms of the materials, wages, and the balance is needed. The time is spent on the replacement and the saving obtained by reducing the operating costs. So there are conflicting situations and we have to optimize that at what time they are to be. So our variable becomes the time. So objective becomes to determine an optimal replacement policy that will minimize the sum of the operating and replacement cost per unit time. Per unit time, most of the time we assume that they are to be operated for a long period of time. And per cycle, sometimes it becomes easier to model them on a per unit time basis rather than over a finite time horizon. So most of the models you will find in this area are per unit time basis. So if you see the curve, this is the replacement time. If the time is increasing, so number of replacements are going to be lesser number. So in other words, the replacement cost is likely to decrease if the time to replacement is large. In other words, as I said, number of replacement will be more, but at the same time, it might happen the number of failure between that duration might increase. So failure replacement cost is going to increase. And if we combine these two costs, we have to find out at what point it is going to be minimum, and that is the time at which this to be replaced. Okay. Am I clear?
Clear, sir.
Yes, this figure you try to understand because many of the things can be cleared once you use the. So performance measure, as I said, operating cost is going to high. So total overall benefits we are going to get once we are. So in many situations, what he said, this is equivalent to optimizing the measure of performance per unit time rather than a finite horizon, right? Finite horizon. So more. So short-term deterministic because the magnitude of interval between replacement is in terms of weeks or months rather than years together. As I have given the example for 50-20 years, that is not coming in this category, right? Long-term replacement policy, as I said, that can be used for capital equipment replacement models. Okay, so you see that we have to find out what is the optimal value of TR in one cycle. Of course, number of cycles can be there. In 1 year, if you have to go through 2 cycles, 3 cycles, accordingly, the cost can be linearly extrapolated. Right. So between this interval, we because replacement we are taking place, we want failures as minimum as possible in the sense less than 1. Okay. If more than 1 are failure, then our preventive maintenance policy is not optimal. We try to reduce this so that our operation is not going to be interrupted. So between this period 0 to TR, there is operating cost, right? Operating cost. And at this point, you are replacing it. So total cost of replacement, this not only includes the purchase price of the particular item, but also other costs involved, the labor involved, the wages involved, and so on. Okay, they can be combined, and many other costs can be combined. Okay, so in this cycle, the operating cost is involved and replacement cost. Two costs we are just considering as we have shown in the earlier conflicting situations as well, right? So objective is to find out the optimal interval between replacement. That is, this value is to be find out. Okay, so CTR, the total cost of replacement per unit time can be written as total cost in the interval 0 to TR and length of the cycle. Okay, so this is the modeling we are trying to model the problem. So total cost in the interval, as I stated, that operating cost, which is time varying, and plus the replacement cost, which is on average we are taking it right now, cost net, and length of the interval. Of course, the cycle length is nothing but small t, which is to be optimized. This is the operating cost. We have From past data, you can model it in a function, right? Linear, non-linear, whatever it is, and cost of replacement. So it turns out to be this. This is the final model, which turns out. Is it okay? I don't think this is a very complex model. Okay. So now we have to minimize this cost under the variable TR. What is so if this can be integration is easy, then you can find out this equation, differentiate it using the usual calculus method, and equate it to 0 to find out the value of TR. If it is not integrable function, then one has to use the numerical techniques to find out the solution, or one can also find out using taking the discrete value of TR, that is you are trying to search 1 month, after 1 month, what is the cost of what is the value of this, after 2 months, what is the cost of this, and so on. And you will find at one point you will get the model. So minimize CTR. Okay. Total cost is to minimize. Okay. So this is short-term deterministic problem can be. So at one point you will get this. So if you have modeled the cost in terms of a linear equation, then you can solve it easily. Right. The optimal time turns out to be twice of CR by B. You can just put C of T here in this equation, differentiate it, and you will get this optimal time. Okay, as easy. So this is one example. In this case, the cost is not linear. Okay. So if T is equal to 0, then A minus B is going to be greater than 0, may be interpreted as the operating cost per unit time if no deterioration occurs. You are assuming no deterioration, but as the time goes on, this cost is total cost is going to increase because this factor is going to decrease as the time goes on. So this perfectly models the scenario that, okay, operating cost is increasing as the time goes on and the item is aging, right? Okay, so under this circumstances also, now how to solve it? You are going to get the nonlinear equation. As I said, if you can integrate it, you can use the differential, or you can put different value of TR, and you will get that the optimal replacement is where the total cost of operating a replacement is going to be minimum at 5th month or 5th week or so, whatever time unit one has taken. Is it okay?
Sir,
So I don't think that this is a critical model for deterministic. There are more deterministic model one can go using higher mathematics, but for the simpler case, one can use this example, right? So there are certain, the answer is not the final objective. We have to analyze also, isn't it? Post analysis based on the real. So most often it is not unreasonable to discard the replacement time because it is usually very small, but one can also take into account, which we'll see that how they can be taken. Besides, any costs, such as production loss incurred due to the duration of the replacement need to be incorporated in the cost of. So as I said, CR, capital CR, the cost of replacement we are taking on an average constant value. One can include as many cost in that cost itself on an average. What is the cost of replacement, wages, and so on, and lost production also one can take. Besides, you find out an optimal time, okay, 1 month. There may be considerable difficulty in scheduling replacement to occur at their optimal time. It may be possible that, okay, the production is on, one cannot stop. Right. So what is to be done? One can draw this kind of curve at what is the total cost if the replacement is done at various time. So most often you will find a shallow curve at the bottom, right? So if somebody is doing maintenance, opportunity is arising. So one can do replacement here also, one can here also, rather than exactly at this point, one can defer it. So management will also, you cannot, one can also explain to the management that there is not much difference if we defer it or prepone it. Okay, so these curves are going to be very helpful while this. So the advantage, as I said, along with giving the optimal value of TR, is it shows the form of the total cost around the optimum. Okay. So the curve is fairly around flat around the optimum. It is not really very important that engineers should plan for the replacement to occur exactly at that point of time, thus giving some kind of leeway. Okay, partially. So this is just, so in this case, you see that between 3.5, around 3.5 to 6 weeks, there appears to be not much difference. Okay. So however, the total cost curve is not fairly flat around optimum, but is steep rising, then optimal interval should be adhered to as much as possible. Right? Like V-shape kind of curve, we don't have much leverage. Optimal is coming like that, so one has to do it because there is a steep rise in the cost if we go beyond that. So if the time required to produce affect the replacement, so one can say that, okay, this was the original cycle, now it is the time at which the replacement is to be done, then the cycle length becomes TR plus. So cycle length is changing. Operating cost is only coming into this picture, right? Operating cost is up to this only, and the replacement time increases the cycle length and the cost of replacement coming. So just incorporating this, the model changes too. Okay, so cost of replacement, say cost of replacement here. This is the operating cost, replacement cost, and the cycle length now becomes this. So replacement time can also be incorporated with a slight change in the model. As I said, one can relax the assumption to make the model more serious and which depict the scenario which we observe in real life. Okay. Many of the time, as I said, integration is not possible. So this is one of the example. You please solve it by yourself. Although solution is done, most often I also make the mistake while solving it, right? So this is the data which is given that the filter cost is $80. The automobile driver travels 2,000 kilometers a month. This is a statement of the problem. Whenever you are studying a problem, one has to make a statement so that that can be understood very well to model it at a later. So when the air filter is new, then during the first month of operation, the automobile performance is 15 kilometers per liter. Thus, the first month's operating cost is 100. You can compute it. Okay, it's not coming out. This is not a very difficult task. One can compute it, and of course, there is no function, operating function is not. We only know at discrete point of time the cost is again. Okay, so how to solve this equation? One can find out that first month the operating cost is turning out to be 100. Next month it is turning out to be this. So this is the value of the operating cost at different point of time. Okay, so one can compute the total cost in each month. So this is 180. One can plot also 43, 134, 131, and this point you will find the minimum operating plus replacement cost. So your time becomes fourth month. Okay. So this is the way one can also solve if they do not have any cost function or we cannot model it using some mathematical equation. Okay. So right now, I know that you are unable to understand this. So first is the operating cost, which turns out to be 100, and replacement cost, and per unit 1 month. Right. And in the second month, the first month operating cost, and the second month operating cost, and 80 remaining say the replacement cost divided by per unit cycle. Cycle length is now 2 months. So you will get this way. Likewise, you will have to incorporate the previous month's operating cost and per unit cycle. You will do. Okay. Is it okay? The calculation part, you can do it afterwards also. Okay.
Sure.
So try to resolve it first by yourself, then see the calculation which has been depicted in this slide also. Okay. So that is one example just chosen for deterministic, but most often we are not dealing with the deterministic replacement model. We go for the stochastic preventive replacement model. Okay. So with the uncertainty, I have already stated that impossible to predict the failure when the failure is going to occur, the transition from good state to the bad state or any other state which is not desirable. Impossible to determine the actual current state of the equipment unless a certain maintenance action such as inspection is to or assessment of certain parameter is done and so on. And binary state model, that's why we take, right? So optimal sequence of time, we have to find out at which the replacement are to be occurred by minimizing or maximizing certain criteria. As I said, that criteria in our case could be minimization of time, downtime, maximization of profit, minimization of losses, and so on. So any criteria, they are interrelated also. Minimization of downtime implies maximizing availability also. Right. So as condition has been assumed, right? Whatever action we are taking in this model, whether this is repair action, overall action, any action which we are taking are assumed to be bringing the system as good as new, right? That item is another criteria which must adhere to, which also I stated, the total cost of replacement. So whatever preventive replacement you are carrying out, it is lesser costly than the post-failure scenario. Okay, post-failure scenario, the cost is going to be very high because that is unexpected, hence mobilizing of the resources and other inventory, etc. control has to be making that cost very costly. While if we are taking scheduled kind of maintenance, we know, we are aware of, we have to take the action on this time, so we are well prepared. The spares are available, manpower is available, the resources, other resources, tools, technique, or everything is available. So corresponding time and cost is going to be lesser as compared to the post failure. And this is related to the yard function. We can do only replacement of the maintenance actions in the third zone, because in the first zone and the second zone, maintenance are a wasteful time, right? Not only resources, all the cost and all the resources are. Right. So this is just, we have already proven in our previous lecture. The third zone is our area where the maintenance action, such as replacement, is to be taken place. So coming to the problem, an item sometimes termed as LRU or part is subject to certain failure, and thus when failure occurs, the item has to be replaced. Because failure is unexpected, it is not unreasonable to assume that a failure replacement is more costly than a preventive replacement. So assumption F appears to be true in this case. Now to reduce the number of failures before preventive replacement to occur at a specified interval, but balance is needed. Again, you see the two curves. On the x-axis, we are trying to find out the preventive maintenance time. Right. So if the preventive replacement are occurring at large value, right? Preventive replacement cost. So if the time is large, you're doing less number of replacements, so preventive replacement cost is going to decrease. Right. So number of preventive replacement are less. If I translate in terms of the downtime, so preventive replacement downtime is going to decrease if we take the large value of the replacement time. At the same time, the larger the time, then it is expected the number of failures might increase and the corresponding downtime due to failure replacement might increase. So you can draw this curve whether based on the cost or whether based on the downtime. So now again the balance, we are just taking these first. So we have to optimize these two conflicting, because one is increasing, another is decreasing, and we are to find out an optimal time where the total cost is going to be failure replacement cost and preventive replacement cost is minimum as possible. This is known as age-based. This is again the similar figure. At when the item is acquiring certain age, we replace it. So same scenario. Okay, so this is a bigger picture. Just that item is here. The item has failed. We have done the failure replacement, and it is living up to a certain age known as TP, which we are saying that this is a replacement time. Preventive replacement is done. Again, it fails. Then again, when it lives up to, right, there is a possibility there is no failure occurring in between this, right, the TP time. So this is the cycle as it is shown in these figures. Okay. This figure, I hope it is okay. Is it okay?
Sir.
Great. So again, similar figure in Zoom. Balance the cost of preventive replacement and against their benefits. This is just. So assumption in this equipment will be operated for a long period of time. As I said, we are trying to find out the optimal solution per unit cycle, per unit time or so. Intervals between preventive replacement are very short. Otherwise, discounting approach, which I mentioned that because inflation, deflation, and the money is changing over a period of time is to be taken into account, because optimization without taking discounting and with taking discounting is altogether different. They will give you different results. And if you get the same result, it is just accidental because of the data which you have taken. Otherwise, they are going to give you different time. So the following costs are assumed. Right now we are taking average cost, right? They can vary also. No issue. So this symbol is for total cost of each preventive replacement or maintenance action. And this is the total cost of each failure or corrective replacement. This is another one, right? So whenever the failure is occurring, we are taking corrective action, reactive action, reactionary action also, right? And this is the preventive action means active. You are actively involved. Reactive and corrective, you can see. So these costs may include these are the costs, parts, supply, labor, supplies, overhead, many of the costs one can incorporate in the event. And since we are dealing with probabilistic models, then failure distribution of the item should have been modeled based on the past experience, based on the past data, or whatever, right? So if you see that there could be two possibilities while modeling this problem. One is that we have to replace at is TP and there is no failure occurs between this interval. So it's a good cycle that we are happy that nothing has happened and we have to replace it faithfully and we were well prepared. And bad cycle could be in this cycle the failure occur on or before the replacement interval turns out. Here you already seen that mean time to failure when the item is to be placed at each TP. Yeah, so this is the use of that mean time to failure once the item is undergoing both corrective and preventive replacement. So it has been shown in this figure, explained above, right? So possible. So now these are to be now modeled in terms of the mathematics. So C of TP is the total expected. Now you have seen that we are using expected word, right? Expectation we are computing because we are dealing with in probabilistic domain where the probability of failure is to be computed. So total expected replacement cost per unit time, we're not going for finite time origin. C of TP is denoted like this. This will be total expected. Remember that expected word in this case, which was not used in deterministic case. So total expected replacement cost per cycle divided by expected cycle. Then why expected? Again, one is clear that if the preventive maintenance interval reached, we are doing it, but another is the item may fail on or before this. So expectations are to be computed. That expected occurrence of the good cycle and expected occurrence of the bad cycle. Total expected replacement cost per unit will be cost of the preventive cycle, right? Cost of the preventive cycle, and probability of occurrence of that preventive cycle. So obviously this is going to be probability of occurrences not failing between 0 to the preventive replacement interval. So that is the reliability. And probability of failure on or before the STP cycle because probability of failure and the corresponding costs. Is it okay?
Yes, sir.
So if you understood that, then that becomes very easy. CP we have taken as the cost of preventive and probability of occurrence of that cycle and cost of failure replacement and cost of probability. So this we have computed this part. This is again the same figure. How to model this? Expected length cycle, length of preventive cycle, and probability of occurrence of the preventive cycle. Again, this is nothing but the probability of not seeing the failures and nothing but reliability over a period of time. So this part. And expected length of failure cycle. This is mean time to failure once the unit is undergoing preventive replacement, which is we are denoting as capital M suffix T. Right, which MTTFP has computed for a item. So if you write it, so first is this is a good cycle, no failure has occurred. Then probability of occurrence of this failure is reliability of this item. And then expected length of failure cycle. This is nothing but MTP what I said, and probability of occurrence of this, which is failure on or before this time. So this is the region. Okay. So this is what you have done earlier, right? In the earlier lecture, this was the case, but mean time to failure of a truncated distribution. Right? Expected time of failure of the unit undergoing a preventive maintenance cycle. Write this. This is the model. This is the final equation which turns out, of course, it becomes complicated based on the reliability function, based on the MTP function. Okay. So slide. If you open this, if you write the value of this and you solve it out, let's simplify it, you will get this. And this entire equation turn to the denominator turn to this part, which is the same as you have done earlier, and CP, RTP, and CM. Okay, little bit, say you can integrate it by parts. You will find this can be this are going to nullify because of the solution of this equation, and you are going to left with this simple integration, nothing complicated involved in this. Okay, so you can either express this model with this or with this or with this. Okay, I hope I am clear. Is it okay?
Sir,
So this I have already, this is mean time to failure, and reverse of this is total failure rate, which constitute of two parts. Rate, this I have already explained in that list, right? In other words, if you say the expected number of failure when stabilized constant failure rate is considered, for a constant scenario, the expected number of failures are given as lambda into t. So here, expected number of corrective replacement and expected number of preventive replacement. Okay, so lambda c, lambda p, you can always have, right? Or if you are taking the time also, operating time per unit time, of course, you can divide it by t. So you'll get the same equation as you have done earlier, right? So you can drive this, the earlier equation, using this stabilized corrective failure rate and the preventive replacement rate. Same model. It is per unit time, you are going to get the same equation. So if you are lucky, you can use the calculus, differentiate this equation and find out, equating it to 0, to what will be the optimal TP if you are lucky, right? But most often this is not the case, and one has to resort to the computer or some graphical solution, right? But these are the equations for the model which I am discussing now. Remember that for various value of a minimum will only exist. So first check whether the cost of this preventive replacement is lesser than this value or not. If it is not, you are not going to get the solution of that equation, because the assumption you have made that cost of preventive replacement is lesser than the post failure replacement cost. Okay, so remember this. Okay, so if this is the case, then better you say that there is no need of preventive maintenance at all. Run to failure and replace it. Okay, cost based consideration. Okay, so this is just if you want to check what reliability goals you have and what reliability you are going to achieve, which we have also seen in our earlier lecture, to find out, to use the approximate formula to find out the reliability under preventive maintenance with stabilized corrective failure rate. कि चलिए ये one has to adjust the preventive replacement interval if the reliability goals are not met. This is just this slide. So this is a very short example. Suppose this is CP is given, CF is given, and it is a desire to determine the optimal replacement interval subject to replacement strategy. And the failure distribution is normally distributed with mean 5 and deviation, standard deviation of 1b, right? So one can use this equation. Okay. So you'll get the cost at different interval. So fourth week is appears to be the time at which the minimum cost per unit time will occur, which is $1.50. Okay, so this is just the glimpse. If you're really interested, you try to solve and see that what difficulty you face. You will have to refer the normal tables, or you will have to use your calculator to find out the CDF, isn't it? All things you will have to do it. So this is one of the applications. One was asking that what to do. Suppose the previous history shows the item has failed. First failed as 12 hours when it was replaced here, then it operated for 33 hours, then 9 hours. So to the data, you know the failure data, and this is to be modeled. And when modeling is done, then we have to see that what beta is coming out. Okay, so in this case, variable analysis is sorted to, and it is found that it's 2.97. So it is varying very quickly, and the characteristic life turns out to be 17.55 weeks. So one can compute the mean time to failure of that. Okay, so see. So replacement is was identified as 14 weeks. Here, once the data was analyzed, the minimum is occurring at 14 weeks, right? There are again observation. This is the way one can present that the cost per week and the this replacement intervals, and one can show that it is minimum, or one can see that this is also, if the cost is not very much, then one can say in this interval, one can take the necessary action for replacing it. So in this case, you will see postponing the preventive replacement is past 40 is becoming very high costly. The cost is increasing drastically. On the other hand, if you do the preventive maintenance earlier than 10 weeks, you are doing over maintenance. Right? This is what the question was asked. The manufacturer has said that you replace it after 6 months or so, then whether now how to ascertain that we are doing over maintenance or under maintenance. This can only be ascertained once we analyze the data. If we have, then only one can say quantitatively, yes, we are doing over or under maintenance. Is it clear? The participant who was asking that question earlier. Hello? Hello? Because earlier the question was asked. I hope that this answered the question, because one has to analyze the data first, then only one can say that. Another aspect, one has to deal with the sample size. Statistically, we call that a small sample size is 5, moderate sample size 20, and more than 20, 25, 30, we can say, okay, the data is sufficient statistically to provide a good answer, good modeling in terms of the distributions also. Right. So whenever such is the case, then confidence intervals are usually plotted. And in that case, one has to ascertain that the beta value is turning out to 2.97. If we are trying to find out the confidence interval of this beta value, it should not contain the beta value of 1. Then there is a possibility that the random failures are occurring. There could be the reason, other reasons, not because of the item, right? So one has to investigate that also. Okay. So switching on to the next model, if something is missing from the previous model, please do ask me. Hello? Any question from the previous model? Hello?
Audible, sir.
So coming to a slight change in the previous model, in the earlier case, we are doing failure replacement. Now we have assumed that this time is almost negligible. So we are not considering this. Likewise, whenever the item is ages to TPRs, where we do the preventive replacement, we have assumed this time is negligible. Hence the previous model. But suppose the time somebody wants one should also include this time also. The model changes, everything remains same. The statement of the problem, the cost we have to consider, everything remains same, except that now we are considering this also. Mean time required to make a preventive replacement and mean time required to make the failure replacement. Okay, these times are to be taken into account and this is remaining same. So this all statement, problem, situation remaining same, except we have to consider these times, they can easily be considered. Okay, same statement, nothing is to be changed. Now, this is the good cycle where preventive replacement is occurring and there was no failure between this cycle, and time to effect this preventive replacement is TP. Where in this cycle, incidentally, failure occurs on or before the preventive replacement cycle, and we had to replace it here, and there was a time loss of TF time unit. Okay, so the cycle's figure also changes. And now based on this figures, one can select same equation, total expected replacement cost per cycle, expected cycle length. So the numerator does not change. Okay, occurrence of this preventive replacement cycle, that not failing, probability of this is turning out to be reliability of this item to period of time TP, and the cost of preventive replacement and the cost of preventive failure replacement and corresponding occurrence of that cycle. Okay. Changes occurs in the denominator side, length of preventive cycle. Now see, the length of the preventive cycle becomes this way, right? And length of wet cycle becomes this way. So multiply this cycle with the probability of occurrence and probability of occurrence in this cycle, you will get the modulus reading. Okay. Okay, no issue, I think.
Sir,
This gives you the final model. Now this cannot be reduced. In fact, earlier you were able to reduce it. Unfortunately, you will have to see whether it can be reduced or not. Slightly denominator. Slightly you can reduce it, the denominator, not fully as in the earlier case. Okay, so just a very small, the same example is extended to where we have taken the preventive maintenance cost 5, failure replacement cost 10. Failure distribution is very normally distributed with mean 5, standard deviation 1, and replacement time is TP and TF. Both are equal. That you do preventive replacement or whether you do, you can take different values also, right? One can take. So this equation can be formulated and one can find out the 4th month or the 4th week is going to be the outcome. Now you will say, sir, both have given the same answer, why to go for this? Isn't it? So as I said, this is not always the case. The model can provide different answers. It is accidental or by chance you get this same 4th month because of the data which has been taken. Otherwise, they should have different value. So this is just a sample calculation, right? For 3rd week, how one can compute, these are the values. The similar calculation can be done for other times. Just a sample which is done. You can check it whether you are going to get this value. You can do it for other preventive replacement times such as 1st week, 2nd week, 4th week, 5th week, or 6th. So the earlier models, we have taken the minimization of cost, incorporating failure replacement time, preventive replacement time, or almost neglecting them. Now, another criteria, many of the situation, what happens, it is we are unable to bring the cost. We are unable to find out the cost of the particular item from the databases, or the company or the organization is not willing to provide the cost. Then there could be another criteria. If we minimize, our objective becomes how can we minimize the downtime, right? So same model, we are just now replacing downtime with the cost criteria. So similar, if the preventive replacement frequency increases, there is an increase in the downtime due to this preventive replacement, quite obvious. But at the same time, the reduction in the downtime due to failure replacement, because you are frequently doing preventive replacement, it is less likely the failure is going to occur within that interval. So one is increasing, another decreasing, and hence we have to find out solution which balances these two conflicting scenarios. So say in figure, okay, there is no change, earlier figures. Now the left hand side changes to downtime per unit time. Earlier that was the cost, total cost per unit time. Here becomes the total downtime per unit time for preventive replacement once the item becomes or attains an age of TP. So now there is a possibility it does not fail, right? The downtime associated with this is because we are doing preventive replacement, downtime is occurring TP, and occurrence of this cycle, the reliability. Downtime associated, if at all failure takes place, then the downtime associated with this failure replacement is TF, and probability of occurrence or probability of failure of that item on or before TPR. So this becomes your numerator, and expected cycle length as in the previous case, considering the time to do the preventive and failure replacement. This is nothing but downtime associated with preventive. And this, understood this, then you have got the model. Okay. Nothing else. So this is another model which takes into account the downtime. Okay, so this is just a small numerical, although it is going to take at least for you 25-30 minutes to solve it, to find out, to get this table. At least 25-30 minutes it takes to do all the calculations. Not less than this. Okay, using your calculators. Okay.
Sir.
So this was application on replacement of sugar refinery cloths. So many things one can. The wonderful thing, the surprise which was observed was when the failure statistics were analyzed. The data was sufficient to analyze the data. There were 229 failures, which is good enough statistically to model it. This turns out to be 1. Now the question becomes, the downtime minimization model was not required, and the conclusion was that best replacement policy was to continue replacing the cloth only when it fails. Because beta is equal to 1, maintenance is not going to give you any benefits. Even if you do the maintenance, it is just going to waste of time and money. But why are cloths failing strictly randomly? Now, okay, the system is on, but the analysis should further see the root causes, why it is happening. So if this question is addressed, perhaps a design or the change in operating procedure may be. In this case, which was taken as a case study, the decision was made to continue using the same time cloth and to continue with past practice, namely to replace the item only upon failures. So this was continued, but one should not stop just getting the data, putting into the software and saying that, okay, based on further analysis is again dated, right? Another component of the same system was analyzed, and that gives the variable 0.8 in the first show. So this was somewhat of surprise because it indicates a high probability of sugar feed failure shortly after installation, that is quality related failure, poor workmanship related failure. Okay. So again, the question is to be why it is turning out to be 0.8. Okay, because the time is not very large or very small. So a worthwhile consideration when dealing with the statistical analysis of data, you observe certain surprises. Okay, then one has to look behind the statistics, the calculations part, the data taken part, right? Everything we further looked into. So in this case study, the data was examined and one find that there was no reason to reject the conclusion that high risk of failure early in the life of the feed, and as it is the risk of failure is reduced. Okay, so again it is falling in the first zone, so it should be replaced only on failure, run to failure criteria. Okay, so the earlier models which we taking based on the item sales, right? One can also take another model as in figure changes. We are replacing the item at each TP hours. Okay. And this policy is related to based on equipment age, not items age, which is going to be replaced. Remember, this is the difference. And the drawback one can find that even if it has failed here, It is filled here, right? So what is done? We have replaced it. In the previous case, unless this item lived up to certain age, only then we are replacing it. But here what you see that it has failed, we have replaced correctly. Again it fails, we have replaced it correctly. And here it has not failed. But we are strictly adhere to that it should be replaced. It might fail very near to this, right? But 6 months has reached, so we have to replace it. Okay. So this is one drawback you can say. So preventive replacement rate one can easily compute FDP. Okay. So same assumptions. Equipment will be operated for a long period of time. Interval between preventive replacement are very short, right? Model ECF, same costs. Right. So here comes, since you are replacing it at each TPR, irrespective of item age, it has been replaced here. It might have more age, might go beyond that, but no, the time has reached, we have to replace it. So here comes the problem of finding out expected number of failures in this interval. Okay. And we want expected number of failure to be as minimum as possible. Okay. So based on this, one can formulate this model as total expected cost in the interval 0 to P, 0 to this cycle. There is only one cycle, right? There is no good bad cycle. And length of the interval. Now you see the difference. We are not using any expected word here. Remember, length of the interval, because we know that once we decide the optimal value of this, that is our interval. There is no expectation. Okay. But the numerator definitely we are to see expectation. Okay. Cost of preventive replacement and expected cost of failure replacement. So this needs expected number of failures. Cost of preventive replacement we have assumed, and cost of failure replacement. And here we need how many failures are expected to occur. Okay. Is it okay? Ajit, is it okay? Any problem in this statement or formulation?
Okay, sir.
And this is one of the area to find out expected number of failures. You will find several approximation, because this problem is not very easy to find out expected number of failure over an interval. So there are various models are existing. Okay. Just to first I say that this is the model which we arrive at. The question in this to answer is how to find out this factor, expected number of failures. So many approximation you can refer the references which I gave, reliability engineering by AICTE, and some research paper also, because I have one of the paper 30 pages which has given around 15 models to find out expected number of 15 to 20 models, right? To find out expected number of hits. If not difficult, if not impossible, it is also a difficult problem in reliability engineering, right? Okay, so one can, depending on if you can differentiate it, find out the solution of the equation thereon, one can find out, right? Do it. Or so in many of the cases, cost, so one can go for the downtime. Same statement, I'm just skipping how you can. This is right. Same TF, same notation, TP. Now here is expected downtime due to failures and downtime due to preventive replacement. So again, for downtime due to failure, it depends on number of failure, expected number of failure during that cycle. And downtime due to preventive replacement, we are not expecting, because at the right time we are replacing it. So there is no expectation and the corresponding. So the downtime due to failure replacement, single replacement, and expected number of failures. So this gives you the total downtime over the intended period and per unit cycle, and downtime due to preventive replacement remains same, right? Because so this is the fourth model in stochastic modeling for finding out the optimal replacement interval for an item which is undergoing preventive replacement. Okay, so some information I am providing you. If FT is known, failure time to the probability density function for the failure times, one can find out the expected number of failure if one can find out the Laplace transform. I hope you have heard of this Laplace transform. Hello? Have you
Yes.
heard of Laplace
Sir.
transform? So Laplace transform, but for many of the situation, the Laplace transform is difficult to obtain because once you have to solve this and then you are to go back in time domain to find out expected number of failures, right? This H star is nothing but Laplace transform of H of t, the expected number of failure which you have denoted. So another, okay, do the approximation. Okay, the derivation you can find out in Alcier book or many other textbooks. You take the mean of that PDF, standard deviation of the PDF. These are only approximation, and it does not mean if this is applicable, this can also be applicable, right? For if the MTTF is, if the time to failure is more than thrice the MTTF, then this formula works. Otherwise, formula for short duration does not work. Another approach is the discrete approach. Okay. I'm just giving an idea. Of course, the derivation is giving in this slide, right? This is based on the renewal theory approach, where Laplace transform is needed. The entire derivation I have given in my slides, which I'll definitely share with you. Another is the approximate formula, right? For each example we have given. For instance, this is normal distribution, which mean 5 is standard deviation 1. And the replacement time is 1000 week. If this is the replacement time, you see that it is not proper because within that replacement time, 200 failures are going to occur. No, that one has to see whether this formula is valid for this situation or this time has to be optimized. Okay. So it is not expected to get such a large number of failures between preventive replacement, and equation 6 is not appropriate and equation 5 is needed, the earlier equation. This is based on discrete approach. You can divide and see that what are the expected number of, suppose the time is 4 weeks, you have divided this interval into each week. Now the preventive replacement is to occur 1 week, 2nd week or 3rd week or 4th week. It is based on that is right. When it is started at time 0, the first failure, if at all there one, will occur during 1st week. And then what are the expected number of failures in the remaining week? Then the first failure occur in the 2nd week and then remaining period of time, or there are the or criteria, right? Probability theory or this might happen. That is, the first failure can occur in this week. And what are the expected number of failures in the remaining? Or what can happen? That the first failure can occur. First failure can occur during 2nd week. Then what is the expected number of failure in the remaining week? Another, or the first failure might occur in the 3rd week. And what are the expected number of failure in the remaining? So based on this equation was derived. Right? There are 4 components. Just 2 later was realized. Okay. So this gives you a recursive equation, right? This gives recursive equation which can be finally for the example which we have taken, for 4 weeks, this is the equation and the simplified equation, and then this can be generalized to this equation. I'm not going to the details of the derivation, except you know that derivation is already given. The idea is you are saying that the first failure occurs in the first week, then what are the expected number of failures in the remaining week? If does not happen, the another possibility, you are considering all the possibilities within this 4 weeks period, and then you are finding out what could be the expected number of failures in this 4 week, and then you are generalizing it for finding out the expected number of failures in the discrete manner. So these are just example using this discrete equation. The solution is also provided. So if you face any problem, again, I'll say you are welcome to contact me anytime. You can get the email address from Dr. Vivek. So this is for the model for time minimization, because we know that how to find out the expected number of failures, right? So expected number of failures was found out for first week, then second week, third week, depending on what interval you are choosing. And then you can solve this. Again, I'll say it is computationally, it is not say 10 minutes or 15 minutes issue. If you are going to solve it, again, it is going to take another 30-40 minutes, because not only you have to solve the equation, this D of TP, but also you have to find out the expected number of failures using that recursive result and so on. Okay. So basically, as far as the lecture is concerned, I have covered the models, but the extension of this could be to find out the spare parts, which one can find out. For example, there's preventive replacement time. Now you very well know the time to failure distribution. You also know, and planning horizon is typically say 1 year, and you try to find out what are the expected number of spares to be kept. Right. So this can easily be find out for the second model. Second model in the sense equipment based. So if the time horizon is T. Okay, so how many preventive replacement are going to occur with this time horizon? So this gives you the preventive replacement requirement. And this gives you the expected number of failures over this time horizon. Very easy, right? So as I stated that expected number of failures can be stocked in based on this. So constant interval model, the last model which you can call that constant interval model, and based on equipment age rather than item series. And for this first model, one can find out this is the time horizon and the expected cycle length. Okay, so number of cycles occurring in this time interval will give you how many spares are to be needed, which caters the demands both for corrective replacement and preventive replacement. Okay, this is just a numerical example. You can solve it at your own time. Just coming to the end. Thank you. So this completes what I wanted to complete in these 2 lectures. Expected the same time. I expecting it will take 3 or 3.5 an hour. So if I count from 7 o'clock, then it is 3 hours. हाँ जी लुइस सो तो नहीं गए सर
No, sir. Hello.
हाँ जी
Yes, Sumit, please.
Sir, only one query. Like when we are considering the preventive cost in the case of maintenance, there may be a case like we also have a downtime while doing the preventive maintenance. So do we consider that cost also, or only the replacement cost? Replacement part.
As I said, the down you can include in the preventive replacement cost, CP which you are taking, you can take many other costs, loss of production also, downtime cost also, because system is not operable during that time when the maintenance is taking place. What is the losses which are occurring? So many of the costs can be included in those two costs.
Sir. To be very frank, sir, never imagined like reliability, as I have never had this as a core subject. So never, always it has been a topic of interest, but never thought that, I mean, reliability can be so vast and so deep, and specifically to be in the field of maintenance. Thank you very much, sir, for this valuable session. Although I feel like this session needed some more time to go through all these slides, and I would also like to convey my sincere regards to Vivek sir, that he has given an opportunity to broaden our thought process, and the way how the reliability can be implemented in different things.
देखो मैं अपनी स्टोरी बताता हूँ. 96 I met with Professor K. Mishra in 96 December. One professor introduced me, and I was working in the area of computer, languages, hardware, this, that. So he started taking classes. As I said, he is father of reliability engineer. Truly, he is father of reliability. So he started, even he was director of that institute. He said, I will take reliability classes. So he started taking reliability classes for BTech. He said, you attended. I never attended. So my other colleague attended all the classes, because I was also not interested in this. As you were saying that the area is so vast, because I was teaching electrical engineering, I was satisfied. But once I started in 1999, then I find this area is very attractive, very interesting, very practicable. Okay, so you just go through some few books and see the exercises, examples, and you can relate it with your day-to-day observations. Oh, as I said, मारुति कह देता है कि 3 बार आओ, 4 बार आओ, 3 महीने का फिल्टर, सब तुमको उसमें मिलेगा. Right? So it's testing area, but only thing is that it is for reliability study, why people are scared of. The initial cost is very high. They do not think long-term benefits. Short-term benefits one cannot see. So reliability testing is one of the areas. Just testing is needed. Warranty analysis, probabilistically, this comes under reliability area. Maintenance analysis, you have seen that it comes under reliability. Maintainability, we have not covered. In fact, I have not seen anything on maintainability. Because through maintainability, through maintenance, we try to achieve the maintainability which is taken care of at the design stage. You can make the reliable, very high reliable system, but if the maintainability is poor, then you are going to lose. So there has to be a balance between reliability, maintainability, then only you can achieve certain availability. Haji, any other question?
Yes. Any other questions, participants? Okay. I think, sir, we can conclude because, yeah, Sanjeev ji, yeah, this is a wonderful session. Sanjeev ji has written that this is a thank you very much for a wonderful detailed session and guidance.
Really, thank you very much, Sanjeev. Thank you, all the participants. And of course, I am thankful to Vivek, because most often I have seen in the last 20 years, at least 20 PhD scholars.
Yes.
Who have graduated from this institute, and defense officer, there are a lot many. But very few people like Vivek who are carrying the torch of no reliability audit. And that is, I salute to him because we are contented with, okay, we are working in the reliability area. Okay. But we are not doing extensively the kind of short-term course we should organize, isn't it? But definitely, as I said, some of the students like who have graduated from this are doing a great service. At least they are proliferating this area. We are just a support.
Thank you. Thank you very much, sir. First of all,
Sir,
I am
hello.
thankful for your time. And with the short notice, you have spared the valuable times. And as you have already
Hello,
mentioned that generally, yes.
sir. I want to
Ah,
just ask, can we
please, please.
get these PPTs because these are mathematical calculations which give some time to understand. So, sir, can provide these PPTs for us to study?
सब कुछ मिल जाएगा बस ये है मैं PDF में right PDF of those
Yes,
slides
sir.
right and if you
Okay.
refer to the references which I have given so whatever you understood you can as I said you can always you are welcome to contact me even if you are unable to get time or so just go through those texts you will find many of the things and many other value added text in those books okay. So don't worry, if you are working in this area, you are always welcome. Not only I will facilitate you, my other colleague will also help you out.
Sir, during the next week offline classes, I am planning to give the book of Charles Sabling to all the participants. Will it be fine, or we can take some any other book?
No, in fact, if you go for other books, then in fact, वो Charles Eveling की book क्या है? गागर में सागर पड़ते हैं.
Yes.
What I feel, unless somebody is working in this area, many of the things they have hidden, but they have given the conclusive remark kind of thing, right? So that is a good starting point to generate the interest. And another thing which is good for Charles E. Eveling is economy. It is well within the distribution.
Yes.
Right?
Yes.
Otherwise, the reliability books are usually 10,000, 15,000, 30,000 issue. एक बुक खरीदने के बाद मैं थक जाता हूँ दूसरे उसके लिए किया हुआ है and one professor has written that book on PHN residual REM. So one book already I have purchased just now 13,000. Another book he is publishing in June already on. That is again costing 16,000. So the costs books are costly. Of course, that's why I have given the references. Even this Al-Said book. Al-Said book is very costly book.
It's
Isn't it? Dimitri's book, of course, Dimitri is no more. That publisher is sending or selling that book. These are very good handbooks. Very good handbooks. And there's Jardin's book, the third edition. I have given the recent edition because I had to procure it because I am teaching that subject. I need that. So earlier, that was 1975. I started with Professor R.V. Mishra. He gave me that book, 1975 publication. Then came 2006. I had to procure that. Now it has come recent, 2021. I had to procure it. There is just one chapter difference. Isn't it? Like Al-Sayed has published just now, 2020 or so. He has added one chapter on resilience. Otherwise, the book is almost same. Okay, so whichever book they follow, these are the book they can start with. Charles Eveling definitely gives an idea. Then they further explore. Then they can use any means download this. Right, people are smart enough to get those books. I have also become slightly smart because I find the book on the net. I will download it, get it print. Right.
Yeah. Thank you, sir. Thank you very
Thank
much,
you
sir.
so much, sir.
Yeah.
So before we end the session, can we have a picture? So everyone who is listening right now, please turn on your cameras.
हाँ जी, इसलिए थोड़ा सा रिफ्रेश हो गया है।
Yes.
मुझे याद नहीं कि मैंने ये पढ़ाया था उस समय, क्योंकि मैं भी तो लर्निंग स्टेज में था ना उस समय।
मैंने अटेंड किया था 2004 जुलाई में ये सब्जेक्ट।
हाँ, लेकिन ये सब मैं
नहीं इतना
एक्सप्लोर कर रहा था कि
Thank you, sir.
आई नो वेयर द व्हाट टू टीच व्हाट नॉट टू टीच।
No, but it is very, very practical, sir, because my dissertation was also around this, and of course, the work also has been around this. So very, very useful. Thank you.
yeah. Thanks, sir. Thank you, sir. Thank you very much, sir.
Sure.
Yeah.
Thank you very much, sir.
Thank you, sir.
Yes, sir. If participants are there, then we can discuss some points which yesterday was asked about the evaluation. Hello?
Yes, sir.
Yeah. So the total evaluation based, it is 10% marks on the attendance, participation in the various activities or the in-question queries is 5%. Article summary is of the 40%. That would be based on the team and the individual report. Reflection of the general 15%. And project or MCQs or test, these are on the 30%. So it is comes around the 100% weightage of the entire evaluation process. And whosoever will achieve 70% marks, they will receive a certificate, and 90% and above with the distinction. So this is the policy of AICTE. First point. And second, I have received couple of requests regarding the test, that it was a very short time and due to some reason, it would be so early to conduct the exam tomorrow. So few participants have been requested to conduct the first exam on the day 1 of the second week, that is the 20th of February, and second exam on the day last 24th of February. So we are going with the revised plan. So first test we will conduct when we will have offline classes at NIT Delhi, and the second will be the just before the valedictory function on the 24th of February. So there will be no test for tomorrow. Any other query from your side?
That should be sir. What about the report you just said? Can you
That
elaborate?
for that format I am preparing right now. Before leaving the office, I will circulate it over the email. So there will be the two format. One is the article report. So whatever article we have shared earlier, 2 articles, you have to write a few points. One is the key principle of the practices, like what are the takeaways or the principal practices during the courses related to the article. I will give the points also, what you have to wrote there. And articles will be discussed on day 1 and day 2. Dr. Padma will take the article 1 and second article I will take. And the second part is the reflection of general. Here you have to note down the 3 key learnings from the FDPs. 3 key lessons are the concept of the idea which you want to implement from this course. And the third will be the implementation plan for your 3 key lessons, how you will implement. So this will be the small 1-page write-up, some are in the bullet form. So I will share this detail today itself.
Thank you, sir.
Yeah. Okay then. Thank you very much. Tomorrow we will have the lecture of the power system reliability. Be taken by the Professor